Hi everyone. This video is the solution for example 2 in the context of the beam moment distribution method. And we're going to just go through the step-by-step to solve for this problem. The first thing we need to do is to lock all indeterminate nodes. In this case, indeterminate nodes are B and C because we don't know their moment or rotation. But we're also going to lock D despite knowing that their moment has to be 0. But it's just for a little bit that we're going to lock it. And we're going to get rid of this lock very quickly. So this D would not count as a indeterminate node. So in this stage, we're going to calculate the fixed and the moments. And now in this specific case, we have concentrated loads in the middle, we have concentrated loads that are not in the middle, and we have UDL. So plenty of equations here to remember. The first one would be when we have a load in the center. So the moments that we have at the supports are equal to FL over 8, being obviously F the loads and L the span, which then in this case is equal to 120 times 4 divided by 8, so that should be 60 in both cases. Now another case that we need is the one with a UDL. So if we have a UDL W, in this case, the moment you see at the edges is equal to W L squared divided by 12, and that means in this case is 45 times 6 squared divided by 12, and therefore we get 135. And then the last one is when we have a load of F applied at a distance A from one of the supports and then a distance B from another support, being L obviously the big span. And in this case we have two different moments. So I just changed this a little bit to the center. In this case, the moment on the left side is F times A times B squared divided by L squared, while on this side is F A squared B divided by L squared. If we substitute in these two cases, obviously A being 1.5, B being 3, and L being 4.5, we get the final answers. Here is 100, and in this one is 50, which makes sense because B is larger, so 100 has to be larger. Okay, so this finalizes our fixed and the moments. Now we can start talking about distribution factors. And here what's important to know is that we need to calculate distribution factors for two different nodes, for B and C, because these are our indeterminate nodes. So let's separate them first. So for node B, we have two bars. We have bar AB and we have bar BC. And then their stiffnesses in this case. Since both of them are fixed beams, the stiffness in this case is 4 EI over L for both of them. So we just need to check the span of these two beams. So one is 4 and the other one is 6. So if we want to know the distribution factors, remember, is the stiffness of the bar divided by the total stiffness of the node. So here we get 4 EI over 4 divided by 4 EI over 4 plus 4 EI over 6. The EI always simplifies. And in this case, we're going to get 0.6 for AB. And now we know that in this one has to be 0.4. So in total, we get 100%. Now, let's look in node C and repeat the process. Node C obviously has two bars in it as well. So we have bar BC and bar CD. In this case, we're not assuming the bar CD to be fixed. As I said, we're fixing this, but it's just momentarily while we're calculating these fixed end moments for D. But you'll see that very quickly we're going to get rid of this moment that shows up here. So in fact, when we calculate the distribution factor for bar CD, we're going to assume it to be 3 EI over L, while bar BC, this one is indeed fixed, we assume it to be 4 EI over L. The length of the two bars, one is 6 and the other one is 4.5. So this is the stiffnesses we have to use to calculate the distribution factor. Okay, same as before, here is going to be the stiffness of bar BC divided by the sum of the two. And in this case, we get that this is 0.5. So we know that this one also has to be 0.5. So in this case, it's 50% of the moment for each bar. This concludes the distribution factors, 0.6, 0.4, and then 0.5 in both. Now we need to do the carryover factor. So the only thing we need to know in a carryover factor is between fixed points the carryover is 0.5 in two directions. Between a fixed pin bar, the carryover is 0.5, but only in the direction of the fixed support, never in the opposite direction because you can't have moments in the pin support. This leads us to the most hard-working part of the problem, which is to balance the structure. So this problem is going to be a bit complicated, a bit troublesome. So I suggest you guys draw a really, really large structure here. So we have plenty of space. So a large structure like this one. So first thing we can do is to put the distribution factors. So we know that for node B is 0,6 to AB and then 0,4 to BC. So 0,6 and 0,4. Let me zoom out. And then in node C, it's 50-50. And then finally, carryover factors between fixed points is 0.5 in both directions. And here, remember, we're not locking node D, so this works only in the direction of the fixed support that we're blocking here. Okay, so that's done. Now, what we need to include is the fixed end moments. So we have 60 for both AB, then 135, so let's write that down. And then for bar BC, we had 100 on the left and 50 on the right. And now before we continue, just check the signs. Remember that these are the positive direction. So moments that look like this stay positive, moments that are counterclockwise are negative. So in this case, all the moments we have on the left side are negative, all the moments we have on the right side are positive. So now I can add minus 60, minus 135, and minus 100. So we're now in a position to start balancing our structure. The first thing we need to do is to balance node D. This is going to be the easiest because of the carryover factor. Whatever happens at C will never get back to D and will never influence the moment there. So the first thing we're going to do, we have 50, and because it's a pin support, we're going to apply minus 50, so then we can add and get 0. When we add minus 50, automatically half gets sent to the other side, and we get minus 25. So then we can add it up here, and then we get 135 on the left, and then 125 on the right, and the rest of the moments stay the same. Now, we could start balance node B, for example, and realize there's a difference here of 135 and 60. That is 75, and we know the negatives are winning, so we need to add positive moments in this case. And now we're going to do 75 times 0.6. That's 45. And we're going to do 75 times 0.4. And that's 30. So once we do this, we will now add it up and confirm that on the left we get 105, and then on the right we get minus 105, which means now this node is balanced. Don't forget to send half of the moments to the other side. So that means here we need to send 22.5 to the left, and in this case we need to send 15 to the right. Let's add it up. Here we get minus 37.5, here we get 150, and here stays the same, minus 125. Now our node C is unbalanced, so we need to balance this one. And again, let's have a look. 150 and 125, this one we can do without a calculator. We know that 150 is winning, and it's winning by 25, so we're going to apply minus 25 in total. And because it's 50-50, we're just going to do minus 12.5 and minus 12.5. This is equal to minus 137.5 and plus 137.5. Now, the problem here, you start understanding what's going to happen next, is that this is going to change. This 12.5 has to be transferred to node B, which will now cause a problem at node B. So this transfer is minus 6.25, and then we can see that node B will not be balanced anymore. So when you have two indeterminate nodes like in this structure, you need to keep doing the balance until you get to such a small error that you can accept the error and move on from that point. So at this stage, we can keep adding and realize that here we get minus 111.25, and here we get 105. Okay, this stays the same, and so let's write it down, and we're good to balance it one more time. So now we can see the problem. Here is at node B, and we have 6.25 of difference, and it's negative, so we're going to do a positive change. And 6.25 times 0.6 is 375, and then times 0.4 is 2.5. We do our addition, and we get 108.75 and minus 108.75. Again, half gets transferred to this side, so 1.88, and half gets transferred to this side, and that's 1.25. Let's do the addition and get minus 35.62, and here we get 138.75, and on this side we get minus 137.5. Okay, we could balance node C again and, send half of it back to B and keep doing this. But here we already have an error of 1.25. And, for the scale of this problem of 100 and something, 1.25 is acceptable. So we're just going to do a little average here and assume the final moment here will be 138.2, which is the average of these two moments. Obviously, the moment that we had there of 0 stays here, also equal to 0. So this concludes the balance of the structure. It takes a little bit of time in this particular one, but hopefully there's nothing too scary. It just might be a bit boring to go through it, but nothing too complex. So now the next step is to calculate the free end moments. And in this case, we're going to go back into the beginning and figure out the cases that we had. So we had a bar with a load in the center. We had a bar with a UDL, and we had a bar with a load that is not in the center. So these are moments that we can very quickly calculate. So if we have a load in the center, we know the moment is FL divided by 4, which in this case will be equal to, so it's 120 times 4 divided by 4. That's obviously equal to 120. In the case of the UDL, the moment is obviously parabolic, and in the center, we get WL squared over 8. It's a very important equation to memorize. Now, with these particular loads, in this particular case, we have UDL of 45 and a span of 6. So this will be 45 times 6 squared divided by 8, and that's equal to 202.5. Finally, when we have a load that is not centered, the easiest way to do this one is to calculate the reactions. And here, remember, we get A and B. The reactions here are FB divided by L, and in this case, FA divided by L. So if you want to know the moment there, we can just do FB divided by L times the distance A. So we get the formula FAB divided by L. In this case, we get 150 times 1.5 times 3 divided by L, which is 4.5. So 150 times 1.5 times 3 divided by 4.5, and in this case we get this is equal to 150. And this concludes this step. So now we have our free end moments for this problem. We can now move on into the bending moment diagrams. This is another case where we need a really big drawing, and usually give some space as well. So let's first have a look at the fixed end moments. So we place them in the diagram. So we know we had minus 35.62, and remember the left stays the same. So here we start with 35.62 on the negative side. Then we get 108.75, and because it's a right side, it goes to negative, so we have to change the sign in this case. And we can confirm with this that it's also going to be negative. So in this support here, we get minus 108.75. In the next support is the same logic. Is here 138.2, and finally at D we know it's 0, as it has to be because it's a pin support. And now what we're going to do is take this shape, the free-ended shape, and place it on top of these moments that we have at the supports. If we draw a triangle on these values, we get something that looks like this. If we draw a parabola, something that looks like this. And now finally, we need to draw a triangle that would look more or less like this. So negative moments are here on the supports, and then positive more or less in the middle of the bars. Finally, we need to figure out how to get these values here in the middle. So if we know that in the middle we get 120, on the positive we need to remove only this average value between these two negatives, and this average value is equal to 72.19. So when we remove from 120, we get the solution 47.81. Okay, same logic now for the second span. We know in the middle we get 202.5, but now we need to remove the average between these two, and here the average is 123.48 When we remove it here we get 79.0. And finally, this moment here underneath the load, we have 150 minus. And now we need to be a bit careful because we're not going to do the average between these two, because the point underneath the load is not in the middle. So we need to figure out what is the value that we have in the position of the load. So let's go back into the drawing in the beginning and realize here that we have 1.5 out of 4.5. So this is 1/3 of the distance, and this is 2/3 of the distance. So now if we go back down, we can figure out that if we take 2/3 of 138.2, we get 92.1. So again, this would be 138.2 times 2/3. So we're going to now remove the 92.1 and get 57.9. So this would be our bending moment diagram, a sketch of it, and the correct one. I can show you the correct one from a software, so you can see that it matches with the software. So now that we're done with the bending moment diagrams, we're going to do the reactions and the shear force diagrams together. And here we have to do the three cases one at a time. So let's start with AB. We know we have a load in the center that is equal to 120, and we have moments in the edges which are equal to 35.62 and 108.75. So if we take only the load of 120, we know to the left we're going to get 60, and to the right we're going to get 60. Now, because of the moment, we know that 108 is bigger than 35, so the clockwise moment is larger, so we need to provide counterclockwise reaction. So down on the left, up on the right. And to get the value of this, we're going to do 108.75 minus 35.62. That's 73.13. We're just going to write it down. This is the difference of the moment, and I'm going to divide by the span, which in this case is 4 meters. And then I get 18.28 for this load, and on the other side I get exactly the same thing, so I get vertical equilibrium. So now I can add up and get 78.28 on the right, and on the left 41.72. Okay, this is our bar AB. We can now move into BC. We have a UDL of 45, span of 6, so our total load is 45 times 6, and if we want to divide it by 2, we get 135 in each one of the sides to balance just the load. And now we need to add as well the moments that we see from the table. So we had 108.75 on the left, and we have 138.2 on the right. Again, the 138 is winning, so the clockwise is winning. That means our reactions need to be counterclockwise, so down here and up here. And now the difference is 29.45. Let's do 29.5. Then when I divide by 6, I get 4.91. Okay, obviously the two of them have the same value, again, making sure vertical equilibrium is still respected. So now we can add on the right, and we get 139.91, and then on the left we get something like 130.1. This gives me the solution for bar BC, and now finally bar CD. This one has a load of 150, and again the distances are 1.5 and 3, and now the moments, we only have a moment on the left. This one is equal to 138.2, and on the right we have 0. So now we can get the two reactions just due to the 150. And now remember, if this is 1.5 and this one is 3, our reaction here on the right has to be times 4.5 to compensate the moment done by 150. So if you take your pivot here on the left side, you're going to see that this is 150 times 1.5 and then divided by 4.5, so you get 50. And that means on the right side we get 100. Now, because of the moment, we have just a counterclockwise moment, so that means our reactions need to do a clockwise rotation. So it's up on the left and down on the right. The value of the reaction have to be the moment divided by the span. So 138.2 divided by 4.5. In this case, we get 30.7, again, for both cases. We can now add and get 130.7, and in this case get 50 minus 30.7, which is 19.3. Okay. Now we have all the ingredients to do our shear force diagram. Let's do it very quickly here. Draw again a very long structure. We can start with the drawing. So we have 41.72 here on the left. On the right, again, remember that this is pointing up. So that means E in the diagram is 78.28 pointing down. So remember the convention for shear force diagram. Looks like this. Both of these arrows are positive. Then we get 130.1 on the left of bar BC. And here on the right, we get minus 139.91. Then we get 130.7. And then finally, 19.3. Now, to do the shear force, the rest of the shear force diagram, we know that in AB, we only have a load in the center. So is this load here that's going to allow us to connect these 2 points. For the case of bar BC, we have a UDL. So in a UDL, our shear force diagram is linear. And again, back into CD, we have a load not in the center. So this just goes 1.5, then down, and then we close it. These ones are positive shear forces, and these ones are negative shear forces. So this would be the sketch for this diagram. Now, in terms of reactions, which we can do now, here we have a reaction of 41.72. Here at B, we have a reaction that takes us from 78.28 to 130.1. So if we add them up, we get a reaction of 208.38. Here at C, same logic. What is the force that gets us from here to here? So you get 139.91 plus 130.7. That's 270.6. And then finally, the last reaction we have here takes us from negative 19.3 to 0. So that's our final reaction. So here in black, these are the 4 reactions that we can calculate in this structure. Okay, final but very important step is the deflection. So sketch of the deflection. And again, I'm going to draw it next to the bending moment diagram because these two are connected. So I'm going to draw a big structure again and now use the bending moment diagram to draw my deflected shape. So I know that when I get negative, my bar is unhappy, so it has tension on the top. And I know when it's positive, my bar is happy, so it has to have tension on the bottom. So again, here I have to have rotation of 0. Here I have to have the deflection passing through these 3 points, but nothing on the rotation. So if it starts going down, then I know this has to start going down here. Let's zoom in. Then it becomes positive. That means the bar has to become tension on the bottom. That's what this part of the moment is telling me. Then again, starts to be unhappy, so tension on the top side, and has to go through that point. And now it kind of looks similar. So back to positive, so back into smiling. Then back to unhappy. So it has to do like this. And now we have to keep it happy until it connects to the support. So because there's no negative moment here, we know that the only way to close this deflected shape is by doing this. Okay? We cannot do this, and then I'll delete it. We can't do this, because to do the green, this part has tension on the top. And if we have tension on the top, we would need some sort of negative moment here, and we don't have it. Okay? That's why we know the green is not correct, and the red is. Thank you very much for watching, and have a lovely day.